Okay, so my name is Mateusz. I work here at Base in Big Data team, and I will give you a short introduction to deep learning, which is a new and powerful way to do machine learning. It will be a really high-level overview, so I won't go into too much details, but I'll give you just a hint what it is. So the first thing is we are a data crack, right? So we deal with data. And we create applications or services that collects the huge amounts of data, right? And this is data of many different kinds. So we have data that represents some business data, we have images, we have text, we have audio. And in order to deal with this huge amount of data, we need appropriate tools. So we talked about these tools here at Data Crack, so the whole big data stack, Hadoop, Spark, Storm, and many others. But eventually, we want to take this data, take this technology stack, and we want to build awesome data products, right? This is our ultimate goal. And for that, we need a third ingredient. And this ingredient combined with data and tools will extract knowledge from data, and we could incorporate it or use it in our product. And this secret ingredient is often machine learning. And of course, there are tons of different machine learning algorithms, right? We have algorithms for extracting data from in unsupervised fashion. So, for example, we can do customer segmentation, we can visualize our data set, we can do some dimensionality reduction. If our data is labeled, we can do some predictions, classifications, for example, build a spam filtering. And of course, by looking at the correlations between various data points, we can recommend something to our users or detect some abnormal behavior in our system. But the point is there are many different algorithms, and some works better on some problems and some works worse, but there is a range of problems that are practically unsolvable by these conventional machine learning methods. And for us humans, these problems are kind of obvious, trivial, right? So image recognition, whether something, what is present on given picture, or whether the two pictures contains the same object, or speech recognition, also very difficult for conventional machine learning. And finally, natural language processing. Most of the data, or maybe not the most, but the huge amount of data is in textual form. So it's really important to have something that works on this kind of data and we're able to draw conclusion from this kind of data. And that's where deep learning arrives, and it just works. So here are some examples of deep learning products. The most recent one, Skype Translator. It's really amazing feature for Skype. Now people talking on Skype can talk in totally different languages, and without knowing the language of the person they are talking to, and Skype Translator will automatically recognize what we said. It will translate it into some other language and then synthesize our statement using our voice in different languages. It's just mind-blowing. It enables communication between peoples that wouldn't normally understand each other, right? The second example of the deep learning product is, for example, Google Plus photo tagging. In Google Plus, we can upload photos, and Google Plus can automatically tag the photos. So based entirely on the image content. So for example, we don't have to tag pictures at all. So it just looks at the picture and it recognizes what's on the picture, and now we can search our own pictures by using keywords. So for kind of person that has a lot of pictures, it's extremely useful because he can browse the pictures and quickly find the relevant ones without tagging it manually. And there are a variety of other products based on deep learning. So for example, voice recognition in Android, Apple Siri, Baidu's image search, and more coming in the future. So first thing, a bit of theory. Deep learning is basically just a bigger and better approach to neural networks, which are for a while with us. So if you're not familiar with neural networks, I will give you a really short introduction. So, of course, we have our data, so-called feature vector. And now in the most simplistic version of neural network, we have a single neuron. Each unit in our feature vector is connected to this neuron, And each connection or edge has a weight associated with this connection. It's just a real number. And then what we do is we multiply the input by the weights, and now we have an input to our artificial neuron. Then to compute output, we take some nonlinear function, so here, for example, a sigmoid function, and we apply this function to our input. So that's the single neuron. Simple as that. But of course, we can have multiple neurons, right? So each neuron has its own connections and from the input vector. And now there's the part where the deep part is coming. So we have multiple layers of neurons. And we take the output from the previous layer and treat it as input to the next layer. And that's how we build a multi-layer neural network. So those of you who knows neural network, you wonder what changed in the 80s. So first of all, now we have much more computing power to train large networks. For serious tasks, we need a lot of CPU and memory in order to train it efficiently. So that's what improved significantly. The second thing is we developed better algorithms for optimization and other things. So our models less overfit and underfit. The third thing is now we can have much more reliable data. So deep learning is particularly hungry for data. So with more data, it works significantly better. And there is also a new way of training these models without using labels. So intersection of these things, and boom, deep learning is born, and it took over a large piece of machine learning tasks, becoming state-of-the-art, if many of them. So that was a really short theory introduction. Now, why it works conceptually? Let's consider the problem of face recognition, right? For us humans, it's simple. We just see a face and we instantly know that it's a face. But for machines, it's a totally different thing, because what machine sees is just a row of numbers, right? So intensities of particular pixels. And if you think about it, it's really hard to infer anything from just raw pixels. So if somebody says to you it's a bit black in the left corner and white in the middle, it's not that easy to guess what it is, right? And with deep learning, we can take these raw pixels, raw data, to our model, and we can extract more abstract features from this, right? So, for example, in the first layer, we can extract simple edges or simple shapes like small circles and something like that. And in the subsequent layers, we can learn even more abstract features, right? So, for example, we can learn the pattern for eye, for nose, and it seems much easier to infer that something is a face based on that it has two eyes and a nose than from the information that it has some black pixels somewhere there and white pixels somewhere else, right? So that's why deep learning works really well for this kind of problems, where we can kind of like hierarchical structure. And a bit of practice. So the major issue with deep learning is that it's really sequential. Single operations can be parallelized, but the whole training pipeline cannot be trivially parallelized, right? So there are two practical approaches to deal with this problem. First is based on GPUs, and the second is based on regular clusters. So first thing, GPUs. Well, GPUs are really efficient for numerical operations. There can be up to 100 times faster than CPUs. And most of deep learning single operations are operations or large matrices, right? And these operations can be trivially parallelized. Second advantage is that it's a single machine, so there is absolutely no communication overhead. But on the other hand, single machine enforces some constraints, right? We cannot train really large models because we don't have enough memory, and we have to stick to the smaller ones. But we can take advantage of multiple machines, but it's somewhat different settings. So deep learning algorithms have a lot of parameters that have to be tuned for the particular problem. And if we have multiple workers, we can assign the same task to each of these workers, but with different parameters. And then we can evaluate all of the learned models and pick the best one. And that's exactly how Netflix does it using deep learning for recommendations. On the other hand, the cluster approach, well, we can train much bigger networks using a cluster. So here's an example of big neural network. But the thing is, we have to restrict connectivity to reduce the communication overhead between the nodes. So here the units are connected only to some local neighborhood. And now we can split this network to multiple workers. And because of the reduced connections, we have less communication overhead. There is another trick with asynchronous parameter server, but I won't get into details. And that's essentially how it works in a cluster, and that's how Google does it. It has some advantages. Of course, we can train much larger models. We are not constrained to single machine memory. It's more scalable, but it's also more complicated, and even that we restrict the connectivity, it's still a bottleneck, right? So it's a poor resource utilization even if we restrict this connectivity. So that's how people implement it in practice, and there is a lot of hype around and publicity around deep learning. So here are some examples of headlines from various tech sites, and by the way, it's both in the industry and the academia. And also major IT companies are investing a lot of money into deep learning. So, for example, one of the leading researchers in deep learning, Geoffrey Hinton, his startup was acquired by Google. The second one is particularly interesting, DeepMind. All they did was that they created an algorithm for playing all Atari games, and they were bought by Google for $400 million. So quite a success. And also some other startups and leading researchers in deep learning are starting a new artificial intelligence labs or are acquired by various companies. So there is a lot of hype around deep learning. And but it's not a silver bullet, right? It has some limitations. First of all, it's really difficult. It requires substantial expertise, and it's hard to implement it correctly. So sometimes it's better just to use the simpler method that will work fine enough for our purpose. And the second thing is, as I said, it requires substantial computing power and memory, right? So it's not feasible, especially if we have to retrain our model on some regular basis. And also it's kind of black box, so it either works or not, but sometimes it's really hard to infer, for example, what the model learned and gain some conclusion from it. It just does its task and we don't know what's inside. So that could be a problem. But nevertheless, it's a very powerful technique. It has attention of the biggest IT companies, and it's certainly good to know it and learn about it and implement it in our problems. Yeah, so that would be all. If you are interested in this topic, here are some resources that you could dig in. And thanks for the presentation, and I will be happy to answer your questions if you have.
Yeah, I have one. Do you know any applications of deep learning in adaptive user interface?
User interface?
Adaptive user interface.
Adapt user interface? No, I'm not aware of such applications.
Yeah, okay, so the next question is about you just mentioned that there is a problem within the verification of the trained model.
Yes.
Just if you can give an example about that, maybe you have an experience such what was the particular case?
Sometimes it's easy to infer. For example, if you deal with images, you can easily, like I showed you on some slides, you can easily look at the hidden units and say that it learned to recognize, for example, an edge, right? But the whole process is automatic. So this particular neuron decided from the data that it should learn this particular feature, right? So we have no control on this, and sometimes it just learned something. It's useful, it's contributing to the whole problem, but you can't easily tell what it is, right? So that's the deal. I dealt with images mostly, so I hadn't bumped into this issue, but that's the known issue in neural networks.
Thanks.
Any further questions?
Do you know any areas where black box is an issue in that case? Because my understanding is we know what is on the input. We are teaching the network to process the data based on the known results. So in theory, black box functioning shouldn't be a problem for us.
Right, but sometimes you are just curious, right? So what makes that something is classified as some class, for example? So if you are curious about this, you cannot tell from this model.